We've been talking about gas laws, and we talked about the Boyle's law and Charles' law, and briefly in an example, the combined gas law, and we also talked about the ideal gas law. And those were all relationships between pressures, volumes, temperatures, and amounts of gas. And now we're going to talk about another gas law, but this one's kind of different. This one's Dalton's law of partial pressures, and this has to do with mixtures of gases. A weird thing about a mixture of gases is that each of the gases in a mixture acts like it's the only gas there. And so the total pressure of a mixture of gases is equal to the pressure of each individual gas. And this is a little bit like mass, in that if you have a box of rocks, what's the total mass of that box? It's the mass of each of the rocks added together, right? So the total pressure of a mixture of gases is the pressure from each individual gas. And we call those partial pressures. And this is true because the pressure of a gas is affected by the number of particles. It doesn't matter what the gas is, because there's so much space between the particles. It has to do with the number of particles, which is related to the moles of particles. The pressure of a gas is independent of the nature of the particles. It just has to do with the number of the particles. So here we have an example. This container has 8.4 atmospheres of pressure. It contains 1.75 moles of helium. And here we've got the volume and the temperature. In these other two containers, we have the same pressure, we have the same volume, we have the same number of moles. So PV equals nRT. But the gases are different. This is a mixture of hydrogen, helium, and neon. This is a mixture of nitrogen, oxygen, and argon. But the total number of gas particles, the number of moles of gases, is the same in each container. The pressure of the container does not depend on what kind of gas is in it. And that's something that's pretty unique to gases. We don't see that with liquids or solids. Does that make sense? So it just has to do with the number of the particles. So, well, I guess I should go back here. No, it's not in there. Never mind. So let's look at this example. This is saying we have a mixture of oxygen, carbon dioxide, and nitrogen gas, and the total pressure is 0.97 atmospheres. What's the partial pressure of the oxygen if the partial pressure of the carbon dioxide is this much and the nitrogen is that other number? Well, let's draw a picture, because sometimes it helps to draw a picture of these things. So here's our gas container, and what do we have in there? First line. We got carbon dioxide, and we've got oxygen, and we've got nitrogen, right? So we have three gases in there. Dalton's law of partial pressures tells us the total pressure in that container is equal to the pressure of each individual gas added up. So we could write that out as the P total is equal to the pressure from the oxygen plus the pressure from the carbon dioxide plus the pressure from the nitrogen. There's three gases in the box. They each exert a pressure. You add those up and you get the total pressure. So we're told that the pressure of the CO2, I didn't leave much room here, but the pressure of the CO2 is 0.7 atmospheres, and the pressure of the nitrogen is 0.12 atmospheres. And we want to know what the pressure of the oxygen is. And the total pressure is 0.97 atmospheres. So 0.97 equals each of these added up. How can we figure out what this question mark is? We can subtract. Okay, this is one of those math things where if you don't think of it in terms of equation, it makes a lot of sense to you, right? If there's 10 cookies, okay, and Tommy has 5 cookies and Michael has 2 cookies, how many cookies does Emily have? Right? We can do that in our heads. She's got 3. Because it just has to add up. So that's what we're doing with this type of a gas law. So don't let the little equation freak you out or, make your brain stop working. So we're looking for this guy right here. So that we must have this then. I'm losing my ability to speak, apparently. It must be the total pressure minus the ones that we know, right? Minus the CO2 and minus the nitrogen. So the pressure of the oxygen is going to equal the total pressure of 0.97 minus the carbon dioxide minus the nitrogen. And 0.15? Thank you. And we do the math there, we get 0.15 atmospheres. And then it's always a good idea to ask yourself, does that make sense? Does it seem at all reasonable? Yeah. If we came up with a partial pressure for the oxygen that was greater than the total pressure, that would be kind of ridiculous. If we came up with a negative pressure, that would be ridiculous. Any questions? So we learned some important things from this. That the volume of the individual particles of the gases isn't important. And that the forces of interaction between the particles are also not very important. Because there we had nitrogen, and carbon dioxide and oxygen. Those do not have the same size. The carbon dioxide has 3 atoms in it, and the others only have 2. The carbon dioxide molecules are larger, but that doesn't seem to matter. One of the reasons that we need to learn about Dalton's law of partial pressures is because of a common technique for collecting gases. And we're going to do this in lab, I think on Friday. Yeah, we're going to generate some hydrogen gas. And in order to collect the gas, if you don't have some really fancy equipment, you use water as a tool, basically. So what we do to collect a gas frequently is that we'll take a container full of water and invert it in another container of water. And this water will stay, that container will stay full until we bubble some gas in here. So here we're generating some oxygen gas by heating some potassium chlorate here. And that gas wants to leave. And so it goes through this glass tube and is trying to get out. And here's the end of the tube. And the gas there is lighter than water. And so it's going to make bubbles and go to the top of this container. As it does that, it's going to displace some of the water. And so we'll end up with the oxygen that we've collected from our reaction inside this container. But we don't just have oxygen, because there's water in this. It kind of looks like a jar, doesn't it? There's water in this jar, and water evaporates. And so as we're doing this experiment, some of this liquid water is evaporating, and there is water vapor, water in the gas state that is also present in here with the oxygen. So we have a mixture of gases. We have the oxygen and we have water vapor. And so we need to use Dalton's law of partial pressures to find out what's the the pressure of just the oxygen. The total pressure is the pressure of the gas that we're interested in plus the vapor pressure of the water. And so anytime you have a problem, a question that talks about collecting a gas over water, you need to use Dalton's law of partial pressures to take the water vapor pressure out. Water vapor, the pressure of the water vapor depends only on the temperature of the water. So this is very convenient because all we need to know is what temperature is the water, and then we can look up in a table and see what the pressure of the vapor is, because they've done experiments and they've measured this. So you see at 0, the pressure of the water is 4.579 torr, and as the temperature of the water increases, the partial pressure of the water vapor increases too. And this should make sense because which evaporates faster, cold water or warm water? Warm water, right? Cold water does not evaporate very quickly, but warm water evaporates quite quickly. And this is indicated in this increased pressure. So to find the pressure of the water in the gas state, we call it the vapor pressure of the water, we just look it up in a table. So this is the sort of problem that we might encounter. An unknown gas is collected over water at 60 degrees Celsius. If the total pressure is 763 torr, what's the partial pressure of the unknown gas? So I'm going to draw you a picture again. So we've got some sort of a container. And we got some kind of a tube coming in here, and we made the gas over here. And so we got bubbles coming up, and that displaces the water. So up in here, we have our unknown gas, and because it says collected over water, we also have water vapor, water in the gas state. We have a mixture. The total pressure of that gas is going to equal the partial pressure of the water, we call it the vapor pressure, plus the partial pressure of our gas that we're interested in. And this number they gave us here, that's P total. That's the total pressure. So what do we need to find before we can solve and calculate the pressure of the gas? We need the vapor pressure of the water. Did anybody print out the notes? Can you look it up on the table? Because if I go back, I lose all my writing. It's not in there? Okay. Well, I'll just go back. Okay, so here's the table that we need. So the temperature was 60 degrees. That tells us that the pressure of the water vapor is 149.4 torr. So the pressure of the water is 149.4 torr. The total pressure from the problem there is 763.0 torr. And we know that the total pressure equals the vapor pressure of the water plus the partial pressure of the gas. And this is what we're trying to find. So the pressure of that gas is going to equal the total pressure minus the vapor pressure of the water. So it'll be 763.0 minus 149.4. $613.6. There's two gases. We find the pressure of one of them by looking it up in the table, the water. They have to tell us the total pressure, and then to find the other gas, all we do is subtract. This is one of those types of problems that messes people up because it seems too easy. I mean, all I have to do is subtract that from the other thing? Yeah, that's it. So don't try to make it harder than it is. Any questions?